Hi everyone. Thanks once again for joining today's webinar. We wanted to focus today on simulation and how it can be used throughout the development process to both create geometry, refine geometry, optimize a part for manufacture, and then perform the relevant different types of analysis. The idea then is to iteratively design a concept whilst getting live feedback from the simulation. If anyone does have any problems with audio or anything like that, then just pop it into the chat box for us. Just in terms of introductions, I'm Rob Shropshire and I lead the sales and marketing side of Origin. I'll be running the session today and will be your point of contact moving forward if you do want to chat with us further. I'd also like to introduce Tim. Unfortunately, he can't be with us today, but he has prepared what I think is quite an interesting demonstration, which I hope you'll all find interesting. He deals with a lot of the technical side of customers and pre-sales. So we'll prefer the session is interactive, so do pop your questions in. We'll make sure we get to them at the end. There will be a couple of polls as we go through. We'd love to know how you're currently using this technology, so if you wouldn't mind answering those at the relevant points, that would be great. I'll start with a brief overview in terms of where we think Discovery fits and what the benefits of upfront simulation are, if we didn't already know, and what we think that means in terms of your organization. Won't spend long on that. We'll then get straight into a demonstration after a sort of 10-minute or so intro, and we'll spend sort of around 30 minutes taking you through the software. And then we wanted to share with you some of the latest developments in the product and how it's improved. The last release was actually just last month, so plenty to share with you there as well. In terms of Origin, we've got around 200 customers. All of them are in the manufacturing space. We, I guess, are advocates for design. We advocate for simulation much earlier in the design process. But we also think that by giving design engineers tools, we can also improve the collaboration perhaps between simulation teams and design by providing one common platform which allows both teams to use a tool set which caters for different types of skill levels. As well as providing the software, we provide all the sort of local support and training services here in the UK and Ireland. The solution we will present today takes about a day to learn. Typically, anyone with a CAD background can sort of pretty easily get to grips with the solution. So hopefully, no matter what your company size is, you should be able to adopt the solutions pretty quickly. So I think simulation design is certainly a bit of a buzzword at the moment. You've probably heard that phrase or a version of that phrase, and I think for most people you'll know what it's all about, but for those that don't, I'll briefly summarize. We think that by giving design engineers all simulation tools, we can explore multiple designs, concepts and materials really quickly. We can challenge the design engineer to move towards innovation by providing a safe space to test out ideas, ultimately enabling designers to make the best decisions with analysis. This can obviously mean less costly rework later on if we wait to the end of a development process to run our simulation, and then we find there's a problem. We're going to have to go back to the beginning, which is often quite costly. Changes are much easier to make earlier on in that design process. Perhaps we can have more cost-effective designs. We can optimize the part, whether that's by choosing the best material or even reducing the amount of material that we're using through optimization. So we'll cover a bit of that, and hopefully just sort of using a design that we think is the right design will probably allow us to get it out to market a little bit quicker as we make the right decisions early on. We can often validate a lot of early designs through simulation without necessarily having to spend money on prototypes or physical testing. I'm not suggesting that testing isn't important, but we can certainly do a lot of it through simulation to reduce those product development costs. We also want to make it clear that we're not just about giving design engineers simulation tools, although we certainly advocate it. For us, it's also about using the simulation experts teams more effectively. We know that There's often more designers than there are simulation engineers. You might even outsource your simulation at the moment. So it's not a case of saying we don't need experts, because we certainly do. But a lot of what design engineers are doing is actually doing things like exploring the factor of safety of a part. Maybe we just want to have a quick look at the stress or the pressure, how air flows through a part. These are all things that we can do quite quickly and easily at the design side. And for those of you that have attended these events before, I'll sound like a broken record, but we shouldn't just see simulation as a validation tool. It can also be a marketing tool. It allows you to differentiate your service by bringing something different to the table. Rather than a CAD model, you can show a customer how something is going to behave in real life. You can allow the client to visualize how you're going to help them achieve their goals or solve their problem. So just briefly, I know a lot of people on the call perhaps will have a CAD system already. In fact, everyone probably will. And some of you will be using the simulation embedded within your CAD platform, or some of you might be considering adding simulation onto your CAD platform. So seeing as today we're really focused on almost a dedicated simulation environment, we thought we'd share some thoughts really, whether you agree or disagree, in terms of what we think the differences are and the pros and cons of a CAD embedded platform that has simulation compared to having something that's a dedicated simulation tool. Now, the reality is that CAD embedded simulations to some extent can be quite compelling. I mean, certainly certain types of analysis like FEA has come quite a long way in terms of the functionality that these CAD embedded simulation modules offer. And having it onto your existing CAD license can often be relatively inexpensive. As it's all in the same environment, you'd hope that it's also familiar to the end user and therefore should be relatively easy to use. And I think for those of you, you wouldn't be on this webinar if you didn't have an interest in simulation. For those of you that are going to try and get money from your management team, sometimes I guess it is easier just to ask for a little more with something that you've already got than it perhaps is to go for a different software tool. I think finally, you can't deny that there is some benefit to being able to run simulations and update a model in its native format for a variety of reasons, which you'll all probably be aware of. This is beneficial if the company is driving the design from start to finish and they can pick the technology that they use. But oftentimes you might be asked to deal with customer geometry, perhaps to improve a concept or fix an issue, and need to run simulations on those. So in that case, it can be quite handy to have a dedicated simulation tool which will allow you to import geometry from any CAD source. If we just flip the coin and consider the other side, I guess the advocating for a dedicated simulation tool, I think it's probably reasonable to suggest that a product that has come from CAD to include simulation will never have the breadth of capability of a company that focuses purely on simulation. And I think the question to ask is whether your simulation environment can support the requirements of both designers and CAE engineers or simulation experts. If the answer is no, then you could argue that it would be much more effective to pick a platform that both designers can use and simulation experts can use all in one place to improve collaboration and efficiency. I'd also suggest that many of you will be using parametric based modelers, i.e. a sort of structure tree and driving your design from the structure tree. And obviously they're fantastic for control and detailed technical design. The equivalent is a direct modeler, which is what our product provides, which is much more conducive to rapid design exploration and rapidly making changes to a model or preparing a model for simulation. And you'll see some of that as we go through. Commercially, we do need to think about the total costs. It's true that certain modules bolted onto your CAD provider can often be cheap, but does it have everything that you need? Will you need to perhaps do some FEA, but actually in the future you need to start doing some CFD, maybe you need to start looking at thermal analysis, maybe you need to run some topology optimization routines to optimize parts for manufacture. So I think it's worth being wary of where you're at now and where your requirements are now and where they might be going. Speed's key as well. How long does it take you at the moment to prep a model, to get results, and to iterate a design and get those results back? When you're running a simulation, can you get on with other work, or is the CAD license being locked up and now can't be used until the simulation is complete? So there's a few things to think about. So before we get on to discovery, I guess what we like to do is define what we mean by upfront simulation. To us, it means constantly running simulations in real time, and you're actually driving your geometry based on the simulation results that you're getting back. It means that you've tested multiple materials, you've played around with different designs, and you've run optimization to save weight whilst making sure that it fits in terms of your manufacturing process. What it doesn't mean to us is just giving a design engineer a simulation tool to run a quick simulation once the design has already really been done, to validate something that they probably already know based on geometry that they might have even used in the past. So for us, it's about using simulation to drive better design and not just be a validation tool, because we've got simulation experts to do the final validation for us a lot of the time. So just before I move on to discovery, if you wouldn't mind, it's always useful to understand if you're currently using simulation. Great. It's also great for us. Sorry, I think I lost connection there briefly, so I'll just start sharing that once. Just put some polls on for us to answer, if you could. If you wouldn't mind just filling those in, just to give us a bit of a flavour for what you're using, if you're using it, at what stage, and also who does it, because it might be left to a dedicated team. Hopefully we won't have any more connection issues. Hopefully that wasn't too much of a problem for people, but do put in the chat if it is. So in terms of discovery, let's just briefly explain what it is. It's a single license, so you know what you see is what you get. At its core, underlying everything is a direct modeler, a full CAD package, which allows you to create geometry, or you can import geometry. So whether you're using CATIA, SolidWorks, Inventor, NX, whether you want to import STL files, step files, anything can be brought in, and you can work directly on that geometry within this CAD package, or create it completely from scratch. You've got all of your main types of physics, so structural, thermal, fluids, and a little bit of electromagnetics, although that's relatively new. And then you've got topology optimization. So it's quite common that you would study a part, maybe run some stress analysis on it, and then maybe push it into topology optimization to try and sort of reduce the weight whilst making sure that we're still hitting our targets in terms of the strength of the part. What's interesting about discovery is that there are two ways to solve a problem in discovery. The first is what we call the explore mode, and the explore mode essentially creates the mesh for you. So it does it in the background. You don't see it, you just see results. The simulation is actually being run on your graphics card, so you get very fast results and it's very easy to use. The second way of solving a problem is the refine mode, which is more traditional. It's using CPU-based solvers. It's where you would sort of create the mesh and have full control over that mesh before you run the simulation. So the first method is very quick. It's great for design exploration. The second mode is more advanced in terms of the accuracy that you might get. But it does depend on the type of part, and I guess it depends on what stage you're at in terms of your product development process, in terms of which mode you want to use. The other thing is it makes it applicable to both experts and designers, so you can both hopefully use the same toolkit. It also, if anyone is on the call that does use other Ansys products, Ansys Mechanical, Ansys Fluent, it also integrates with that as well. So that's enough talking from me. Just in terms of your demonstration route today, we'll start off with some design. We'll create some geometry and show you what tools are available for modifying that geometry. We'll then show you how an FEA scenario can be set up and analysed. And once we've refined that design, we'll run an optimization on that. For those that are interested in CFD or thermal analysis, we'll also be sharing a couple of examples of that with you and combining the two to show you how you can combine physics as well. We'll then finish off with some reverse engineering capabilities within the product if you're quite often having to reverse engineer stuff. And then after the demonstration, which will last for about 30 minutes, we will go through some of the latest features and then take some questions. So what I'm going to do now is just turn my camera off and mute my microphone, and I will play this demonstration for you. Hope you enjoy it.
Thanks, Rob, for the introduction. My name's Tim, and I'll be taking you through a demo of the Ansys Discovery software. So we'll be looking at a number of features within Ansys Discovery, with, for example, FEA, CFD, optimization, and a bit of reverse engineering. But to start with, I'm going to start with a feature that I feel is quite often overlooked with Ansys Discovery, and that's the design abilities. A lot of you will already be using a CAD tool of some sort, and Discovery, of course, has the ability to import those CAD tools and that CAD data and modify it and run analysis on it and explore that design. But you can also create geometry from scratch in Discovery very quickly and easily. So, like an example of this, you might need to create a quick component for a particular function, and you know the basic parameters, but want to let Discovery sort of guide you on the optimal design based on the function and forces acting on your part. So what I'm going to just quickly design is a simple sort of bell crank, a simple sort of push-pull mechanism around a pivot. Obviously, because of being time limited, please don't judge me on the basicness of the design, but it should give you a good idea of how Discovery potentially can be used as a very quick and easy design exploration tool. We could then run analysis on this design that I'm going to knock up, and then we can make sure it's fit for purpose, and then we can also potentially optimize it and see what sort of potential weight savings and cost savings we can make by optimization. So we're now going to start our design. First of all, a few things to mention before we start designing. So we've got our design tab, we've got our sketch tools, and we've also got some 3D modeling tools. So you'll be familiar with a lot of these sketch tools. It is based on a direct modeling approach, but we can also turn on history tracking, which will then behave in a more parametric way, similar to your SolidWorks, your Inventor. So this will track all your changes to the model. So I've just turned that on just to show you an example of this and how it sort of works. But to start with, I'm going to start designing. I'm going to draw a line. Let's look at this from plan view. I'm going to draw this line from the center, and I'm going to type in a value. So that's going to be 200 mil. And I'm going to draw another line now from the end of this one. I'm going to give it an angle of 150, and I'll give it a length of 150 as well. So I'll type in both of those, and then I'll just join that back up here, so you can see I've drawn a fairly straightforward triangle. In Ansys Discovery, we can start to constrain our sketches. We can use our constraints and our dimension tools, and we can drive our model via dimensions. So you can add dimensions as such. So you can add all this sort of stuff in Ansys Discovery. I'm not going to focus too much on the constraints and things just for the purpose of time. So I'm just going to start designing, and then we'll go into hopefully build a 3D model. So I'm going to just draw a circle here, and on both sides I'm going to just do this as 45 mil. And then I'm going to draw, let's say 35 mil here. Then I'm going to use my tangent line just to connect these two up. So that's going to be tangent. And I'm going to use my trim away tool just to start to get rid of any bits of curves and data that I don't need anymore. So I can start to delete stuff that I'm not interested in anymore. So you can see, just getting rid of this. You can do like sort of a box select and delete more at once. So that's my shape. I'm now going to use my create rounded corner, so I can round some corners off. I'm going to say from here to here, and I'm going to type in a value of 30. I'm going to do the same here, and do the same for these ones. So finally, I'm going to put a few circles through here, and I'm going to give those ones 30. Actually, I might go a bit smaller. Let's go 27.5. And there. Let's go 20. So that's my my design, my shape. And if I'm happy with that, again, I can go along and constrain this, and then we'll be able to drive it via those constraints if we wish to make any changes, but we can always snap back to our original sketch. But I'm going to go straight into a 3D mode, which is one of these pull tools, and you can see that now my closed curves have created a surface. So the pull tool will allow me to extrude this part up or down. And remember, these same tools can be used modifying other models. So if you are bringing in your models from any other CAD system, we can use exactly the same tools here to make changes and things to your models. So all I've done is use my my pull tool just to extrude this face up. I might want to just create some sort of cut here. You know, again, weight saving. I might think, okay, well, where's going to be the lowest area of stress? It's probably going to be in the middle somewhere. I'm going to go back into a sketch tool and use this time my offset curve. Double click here and just create some sort of offset here, so some sort of cut. We'll round the corners off just because we know rounded corners are better, and let's just do some nice rounds there. So this is my sort of imprint that I want to just basically cut through the part. So I go back into my 3D mode and I can slice that through. Finally, to finish this off, what I'm going to do is just make some radiuses or rads to this model. Let's add some rads to the outside. I'm going to add 5mm to those edges. You can see that, and then I'll do the same here for these internal edges. So I'm just holding control just to select all these, double clicking to get loops, and I'm going to add a 3mm rad there. So you can see I really used the pull tool and just a few sketching tools just to sort of create that shape. So this is my sort of final design. I'm not going to round off these, but you know, you can do. Just to show you quickly the history or the feature tracking. If we show this now, you can see all of our steps taken to actually create this. So for example, the third step here, obviously the thickness is 25. You know, if you want to change that to 30, we can type in 30 there. Go back to my last step and just rebuild the model, and the model will now update to 30mm. So I'm just going to close that. I'll just do a quick measure just to show you. Select these two faces, use our measure key. Shortcut is the E key on the keyboard, and we can see just very quickly that that is 30mm. So you can update your model, drive your model via your parameters in here. So that's our sort of model complete, our design complete. So hopefully you saw the speed of design there. What we can now go and do is actually run some analysis on this. We can run some simulation on this and make sure it is fit for purpose. So that's the next step. So now that we've designed our part, the next thing to do might be to simulate it, analyze it, make sure it is going to work or it is fit for purpose. So we can start to set up our simulation. So if we go now into our simulation tab, we can see we can set up a number of simulations. This one is going to be an FEA simulation, so it's going to be a structural simulation. The first thing we can do is modify our material. If we want to change our material, defaults to structural steel, but we can create or choose any material we want. I'm going to just set an aluminium, let's say T6. So I've just changed the material there. We can see all our material properties if we wish. These are all here, and we can create our own custom materials as well. If you do want access to a large, massive library of materials, you can also add that into Discovery through grant materials. So we've set our material. Now we can start to set up our conditions. So I'm going to set a support on this axis, this cylinder here, and this is where it's going to pivot around. So this is going to be a hinged joint, so it can sort of rotate around this axis. So I'm going to accept that. I'm then going to specify a force. I'm going to apply this in this region here, and I'm going to choose a direction of this force, and I'm going to say the direction is going to be the Y direction. And I'm going to type in a force. Let's just type in a force of, I don't know, minus 500 newtons, because I want it to go in the negative direction. I want it to go down. So that's set there. Finally, I want to create a spring joint, and I'm going to just sort of create a place for this to attach to. Let's just click on my design tab. I'm going to click a point and just sort of go up from here. Again, I'm just eyeballing this, you know. So this is where it's going to attach to. It's going to be like sort of the anchor point, and I'm just going to just create a point there on top of that. So I've created my my point. Go back into the simulation tab. This time I'm going to actually create a spring. This is going to be attached sort of from here to, oops, missed that one, there. Click secondary face or secondary surface. That's going to be attached to there. And then we can specify what kind of spring it is, longitudinal, torsional, and then we can also apply a stiffness value to it. So I'm going to just apply 5,000, and we can see that be applied there. So we've now got that applied here. So now we can simulate our parts. Now we can actually analyze it and get results. So because we're in the explore mode, we can get results fairly rapidly. I'm going to use the solve button here, and within a few seconds we're going to start to see results appear. So first of all, here we're looking at our displacement results. The solution is still solving at the moment, so that's now solved. We can see, hover over here, and we can see that says complete. We can see our displacement. We can view that in whatever we wish. So we can see the displacement. We can visualize this. We can animate it, so we can see that displacement on our part. If we want to look at our stress values, we can go into stress. I'm just going to hide that displacement, and we can start to see our stress values. We can start to look at this in different values. We can see our higher areas of stress. But if we want to know if this is going to fail or not, we can also go into our monitors. We can see here this has a factor of safety of 65. So it looks like it's fit for purpose. It looks like it will do its job. One thing I'm going to just quickly find out, I'm going to put a custom monitor on this part. So you can create custom monitors wherever you want to get results from this. I'm going to create a custom monitor, and the monitor that I actually want is the mass of this part. I want to know how much this part actually weighs that I've created. So I'll select the variable, click in mass, I've selected my solid, and this will just create me a monitor here. So we can see how much this weighs, 0.9 kilograms. So we can see how much this weighs. So because we've got a factor of safety of 65, obviously it is probably fit for purpose. Depending on where it's meant to be used, it probably is going to be okay. We might be able to save some weight. You know, you might be able to reduce this weight by potentially 50%, and still have a fairly high factor of safety. So the tools that we could use to potentially try and optimize our design is in the simulation tab. We have Topology Optimisation. For this to turn on, I'm just going to turn off my history tracking. So I'm just going to turn that off, and then I can click on my Topology Optimisation tool. So we're going to just optimize this part. So we're going to let the software remove mass from where it's the best optimal part. But before we do that, I'm going to defeature this part. So I'm going to give it the optimal design space. So to do that, I'm going to just basically select on some of these radiuses, and I'm going to use my fill tool, which is in the design tab. And this is a great tool for defeaturing, cleaning up geometry. Discovery is another great tool for prepping your geometry for analysis. So that's another reason to use Discovery. So I'm just removing this and giving the part as much what we call design space as possible. So I've got back to sort of a fairly basic shape, and then I can go back into my simulation tab and start to look at my optimization options. So I'll just double click that. We've got our target, and I'm going to keep that as maximize stiffness. We've got our volume reduction target, and we can also add manufacturing constraints. So if you're going to mold or cast this part, if you're going to 3D print it, if you're going to machine this part, you can choose any of your manufacturing constraints here. I won't be turning it on yet, but I'm just going to just leave this as a default. We do have our protected areas, which we can see highlighted sort of red. These are areas where it's not going to remove material from. You can obviously change that, and you can add any other areas protected as well. So once I've got my setup complete, I can hit the solve button, and the part will start to optimize, and we'll start to see material be removed from the part. So as it optimizes, we'll see material start to be removed from the part, and this will happen. So you can just about start to see this starting to happen now. So you can see that material being removed as it's doing its different iterations, and the material will be removed and optimized. So then we come to our sort of finished shape. Once your optimization is finished, you can use this tool here to add the optimized body to the model. So basically this will create a faceted version of that part. So you can see here, this might not be potentially what you want to end up with. You can always use this as a guide. You can always use this to say, where thinner areas can be, where thicker areas can be, where can I remove material from, and you can always back engineer over it. If you want to use this, you can do other things to this. We can always right click on it. One thing that you definitely probably want to do is create a validation simulation. We can smooth these facets just to make it more aesthetically pleasing, and we can also convert them to a solid. So you probably want to smooth them before converting them to a solid, and that can be exported out as any solid format. So in this instance, what I'm going to do is create a validation simulation. I'm going to right click create validation simulation, and that will do this. It looks like, obviously, for whatever reason, my spring connection has been lost, so I'm just going to just remove that and just quickly recreate that. So let's just use my spring tool. This is my first connection, this is my second connection, and just accept that. So that's my simulation done. I can now validate this, and I can obviously see if it still hits my factor of safety targets, how much mass have I reduced. So let's hit the solve button, and you'll notice obviously what we're doing here is actually solving on faceted data. So this isn't actually solid data, it is actually faceted data. Again, that is sort of different. Again, so we can see that we've got a factor of safety of 45.9. I think that was reduced from around 65. So decrease, which we sort of would expect because we are reducing the amount of weight. But still perfectly safe, and our mass has reduced by around half a kilogram. So if this is going to be potentially a 3D printed part, and if you can save half a kilogram per part, maybe it's low volume, but if you're saving half a kilogram, we know metal powder is expensive, then that adds up. If this is a high volume, potentially cast part, and you're producing 1 million of these, and you can save half a kilogram per part, then again, you can see where these cost savings can add up by using optimization to guide you in your design. And obviously, as mentioned, you don't have to use this exact design. You can always use this as almost like a template, and then you can design over it how you wish and let it guide you. So that's just a quick example of designing FEA and optimization in Discovery. We'll now start to look at some fluid simulations. So we're now going to look at a fluid example. We're going to look at a solid fluid thermal simulation, or CHT. We will first set up just a purely a thermal simulation to show the effects on this model with no cooling. Then we're going to add a cooling channel and see the effects that this has, and then we can modify the design to see the impact. So this is going to be done on this model here, which is a traction inverter. So with the electrification of vehicles and stuff, traction inverter is quite an important component. So if you can optimize and get the best design for that, obviously that would be quite useful. So in this design, we've got a few components. We've got the housing, the traction inverter housing, which is this component and this solid. And then we've got a few transistors, IGBTs, which are here. So the first step in this simulation is to apply a heat source to these transistors. If you do want to change the materials of any part, this is all defaulted to structural steel. But if you want to change the materials, very easy to do. For example, if I do want these transistors to be a different material, I've just selected them all there by triple clicking them. Here's my materials, and I can obviously change that to any material I want. For example, if I want to use that as silicon, I can change that to silicon. Now in my tree, I've got my silicon materials. You can see they're highlighted there. And I've got my structural steel. So I won't focus too much on materials, but hopefully that shows how easy it is to set up and use any materials you wish. So the first thing I'm in the simulation tab, and I'm going to be doing a solid thermal. So I'm going to triple click to get the body of this transistor, go to my solid thermal and add a heat source. I'm going to type in a value of 400 watts and hit enter. Once I've done that, my physics tree will start to populate, and you can see my heat one added here. I'm just going to do that for each of these, literally just triple clicking, hitting enter, and we can see each of my 4 transistors now will appear in the tree. So obviously if you need to modify any of these here, any of the inputs, you can do there. So this solid thermal simulation is sort of set up now. If you want to modify the convection default, you might think that's a bit too high. You can do that as well. But hitting the solve button in the bottom right hand corner, we're going to end up with results within a few seconds. So once this is solved, which it already has done, we've got our results, and we can start to see in this instance things like max temperature, which is obviously quite high. We're looking at 430 degrees there. So that's obviously just showing the a thermal simulation on its own, but we can now create a solid fluid thermal by adding a cooling channel. So I'm just going to turn off these results, and the first thing to do is actually extract our fluid zone. So in the prepare tab, we've got our volume extract tool, and this tool works by basically you cap any regions that has any openings. It works on assemblies as well. Then you specify a seed face. You can always use this tool here to preview the inside faces, so you get an idea of your fluid volume or fluid zone that's going to be created, and that will also show you if there is going to be any leaks in the model, so you can identify where those leaks are occurring. And then you hit the tick box, and you will have a new component created called volume, and that's in there now. I'm going to make these two transparent just so I can see my volume, and then I can create my fluid simulation. So if I go back into the simulation tab, this time I'm going to be doing a fluid flow, specifying a flow condition and specifying an inlet. So I'm going to say 2 meters per second, and then I can also specify obviously a fluid value, temperature value, sorry. So I can specify that here, and I'm going to change that. Let's say actually I want that to be 18. So I'll change that, and then I also need to specify an outlet. So I'm going to choose this one as my outlet. I'm going to leave that as 0 pressure and hit the tick box. So again, straight away now I've set up a fluid solid thermal simulation, and I can now solve this. So you can see here, steady state, thermal, fluid, solid, thermal, and this is a steady state. You can actually now do time dependent as well, so we can click here and we can study this over time. So that's just something to be aware of, but this is going to show steady state. I'm now going to hit the solve button, and again in a few seconds we're going to start to see some results, and hopefully our max temperature should have quite drastically decreased. We can see now that we're looking at around 60 degrees. It hasn't fully solved yet, but it has now. So we're looking at around 58.5. So we've come down from 430 degrees to 58.5 in terms of temperature. We can also obviously look at other things such as velocity. So we can also study the fluid zone, and we can start to study our areas. One thing you may be interested in is things like pressure drop, and what happens if you make design changes. Will it increase or decrease your pressure drop, that sort of thing. So in terms of showing design changes, we're going to use some of my modeling tools. So back into the design tab, we've got a number of tools, obviously pull and move. The tool that I'm going to be using is the move tool. And for example, if I want to make a change here, I might want to decrease the size of this wall or increase this channel here. So I'm just going to use my move tool to make quite a drastic change. You can see I've just made that quite big change there. If I open this chart in terms of pressure drop, once this is now resimulated, we'll get a new design variation, and we'll see whether our modeling change has made it better, or in this instance made it worse. So our pressure drops increased by making that change. Obviously we've decreased the size of that channel. So you can again see you can make these design changes. You can obviously change anything in your physics setup, and you get an instant feedback on whether what that design change you've made has been positive or negative. So you're getting those instant feedback, which is a brilliant thing about Discovery and its speed. Finally, in terms of fluid, I'm going to finish off just showing a new feature in Discovery, which is the rotating fluid zone. So I'm going to finish off the fluid examples with a new feature of Ansys Discovery 2023, which has literally just been released, which is the ability to do rotating fluid zones in our fluid flow simulations. This is going to be a very, very quick example, just hopefully giving you an idea of what it can do. Obviously, anyone who's doing CFD with a rotating fluid zone, for example, a fan or something similar, this may be useful. Just a very quick example here. I've got my blade, in this instance it's a mixing blade, and my fluid zone. The physics I have already set up, so I'm not going to go through the setup just because of time purposes, but we've got our inlet, we've got our outlet, we've got our fluid material, and then we've got our rotating fluid zone here, which is set to 200 RPM in my instance. So hitting the solve button, we will start to get results, and again pretty rapidly getting results. Look, we're just looking at velocity vectors at the moment. We can obviously see the our results and the effect of that rotating fluid zone on our results, obviously increasing the velocity. We can show the animation of these if we wish, and obviously you can modify any of these results. If you're just looking to change the magnitude, we can start to look at contours, streamlines, we can look at particles, and we can also look at direction fields. So we can see the results that we can get. So we're looking at velocities, we can look at pressure, but we can also create any custom monitors that we wish on our parts as well, so just be aware of that. So that's just a very, very quick example of a new feature in 2023. We will show a couple of slides of other new features, whether that be on structural or fluids in 2023. And we're going to finish off with a very quick 2-minute example of reverse engineering in Ansys Discovery. It was on the agenda, so we're just going to finish off with that, and then I'll hand you back to Rob. So what I'm going to finish off with showing you is a reverse engineering example. This is going to be a reverse engineering example on a organic shape, but we can also do reverse engineering on more engineered parts or prismatic parts. Just for the purpose of time, I'm only going to be able to show you one example on this model here. If we zoom in, we can see that it's a faceted part. It's triangulated. It's an STL. And we have a number of reverse engineering tools in our facets tab. So we can see our facets tab here. So this tab is dedicated to working with faceted data. If your part needs to be repaired or you need to prep it for potentially 3D printing, we do have a number of tools in this tab that basically do that job, whether it's fixing parts, checking whether they're ready for 3D printing, or whether it's actually modifying the STL data itself to clean it up or shell it out or merge or subtract and split parts up. But the tool I'm going to be showing you here is our auto skin tool. So this is obviously a very organic part. You're not going to be probably creating curves over this part and sort of creating your own surfaces. You can do, but that might be time consuming. You might just want to literally get back to a solid body, a body that can be exported as a solid format, for example, a parasolid, a step, that sort of thing. So the tool that we're going to use here is the auto skin tool. And as it says, it automatically skins a part. You basically choose the part you wish to skin and hit the tick box. And the software will start to work. And we should, in a few seconds, it'll probably take about 20 to 30 seconds, we should end up with a solid body. So what it does is it first sort of creates the segmentation where the curves are. And you can probably see my screen sort of flashing black at the moment, so apologies for that. But then it will create the curves, and then it will create the surfaces, obviously, that sort of the patch surfaces from the curves that it creates. So you can see down here in the left-hand corner, it's generating patches. Again, just flashing black. But generating patches, it's going to have 122 different surface patches that are going to make up this solid body. So it has just completed. This is a solid body. I will just turn on in my display tab the tangent surfaces, just so you can sort of see where these surface patches are. But this is a solid body, and you can obviously turn off them. They are all tangent, these surfaces. So that then could be saved out as a step, as I say, parasolid, and you've now got a solid body. So very quick example of reverse engineering. If you have come to look at reverse engineering, I'm sorry we couldn't sort of show you more. But if you are interested in reverse engineering, please get in touch. We're happy to give you a personalised demo on any of your own data as well, to show you how the tool works in terms of reverse engineering. And with that, I'd just like to thank everyone for attending. This is the demo, and I'll hand back over to Rob to finalise the webinar.
So just as a wrap up, hope you found that interesting. I know we covered quite a bit there. I guess we're just trying to sort of show you how holistic the tool is, conscious of the fact that you'll all be doing slightly different things in terms of what you're designing and which types of simulations that you want to do, but also focusing on some of those CAD tools which are really useful, even if you are just importing geometry from your existing CAD system. I've got a question as well, which I've seen, which I have seen and will get to shortly. So just as a brief wrap up, I think one of the things that we're quite excited about within Discovery is just how aggressive the roadmap actually is. There's literally 2 releases every single year, and we're seeing quite a lot of growth in terms of the feature set. Some of them we've been covered, but just in terms of structures, and for those that might have looked at Discovery maybe 2-3 years ago, it has come quite a long way, particularly around the actual displacement accuracy and being able to deal with quite thin structures. Obviously, the explore mode is sort of meshing the part in the background, so being able to deal with those thin structures is really important. There's also been a fair bit of work in terms of improving the tools available for you in terms of working with bolts and contacts and connections within the model. One of the major enhancements is the topology optimization workflow as well. You've seen a little bit of that today, but there is a bit more in terms of what it can do. Being able to actually add multiple load cases is really useful, and also driving an optimization actually based on a stress target is a really cool feature, making sure that it sort of sticks to that as it's refining your design. So we certainly like that one. Arguably, there's probably been a few more things added on to the fluid side, which Tim alluded to right at the end, but being able to model rotating fluid zones was really important for a lot of our customers, especially if you've got electronics components, perhaps with fans, or you're dealing with pump design. That sort of stuff is really important. And there are also some new compressible flow options allowing you to combine compressible flow with porous media. One of the most interesting developments as far as we're concerned is today we've focused a lot on the explore mode, which is where it's using the graphics card to solve the simulation, and it meshes it for you in the background, so you don't have so much control in terms of that mesh. There is another mode which I alluded to in the presentation, which is a refine mode, which is this idea of actually deciding on the mesh for yourself. So setting up global mesh settings, setting up local mesh settings for particular areas of the part, which is really useful for dealing with complex geometry. What they've now done though is they've allowed you to use the full mesh controls that you would get in refine mode, but actually use the GPU solver to solve the problem. So that is going to enable us to deal with much more complex geometry, but actually solve it with the speed of the graphics card, which is great in terms of getting really fast results. There are more enhancements. You know, some of you might not have seen the product ever until today, so I didn't want to go too much into it. But there are other enhancements around electromagnetics and modeling. So if you have looked at it before, maybe you're even using it at the moment, then there is a hell of a lot more in the product now, which we can talk to you about. And if you drop us a message, we can go through that. Last slide before we break for some questions. Just a bit of a wrap up. I know we've gone through a bit of a whistle-stop tour today. Hopefully we've not covered too much. But you know, hopefully what you've seen is that the tool is quite robust. There are lots of different options for you in terms of modeling. There's lots of options for you in terms of how you want to solve the problem. Do you want speed in terms of GPU solving, or do you want to control the mesh completely yourself? It includes all of the main physics that you're going to need. So you've got your FEA, you've got your CFD, you've got your thermal, you've got topology optimization, and it's all under one license type. So there's not sort of lots of additional modules for you to consider. The final thing is that we think the software looks quite nice. It's quite intuitive. So you know, hopefully you'll see it's quite an easy tool for you to use. I'm going to flash my contact details on there. We will follow up with all of you that have been sort of kind enough to attend. But if there is something that you would want from us, then let us know.